Once the universe was full of mystery, its forces hidden, its laws unknown. But in the 1600s, a new kind of explorer emerged, not with swords, but with clocks, lenses, and questions. Welcome to Uncover Time, where we follow the minds that turned wonder into knowledge and mystery into measurement. Today we explore a moment in human history when the laws of nature were first measured, tested, and written into the language of science. In the 1600s, physics and chemistry quietly expanded without challenging faith directly, yet their discoveries gradually replaced miracles with natural laws. Physics was not born in philosophy, but in the practical needs of navigation, trade, and machinery that demanded better tools and measurements. Sailors urged astronomers to map the skies and begged inventors for clocks that could measure time accurately even while ships rocked on the open sea. Longitude could be calculated by comparing the time of sunrise with a clock set to Greenwich or Paris, but such precision required a clock immune to waves. In 1657, Dutch scientist Christian Huygens invented a pendulum clock, using a swinging weight to regulate time more accurately than ever before. But pendulums were useless at sea. So Huygens later created a marine clock that replaced the pendulum with a balance wheel driven by two springs. This new design allowed accurate timekeeping even on moving ships and was published in his important scientific work, The Pendulum Clock, in 1673. Robert Hooke, another great mind of the age, developed the anchor escapement for clocks and applied spiral springs to balance wheels in watches. Hooke explained that the tension of a spring determines the strength it gives, a principle still known today as Hooke's law. Accurate pocket watches became possible and affordable, allowing time to be measured and shared more widely than ever before. Huygens also studied centrifugal force, noticing that spinning objects stretch outward and flatten at their poles like the shape of Jupiter. He concluded that Earth, too, must be slightly flattened at its poles due to the same spinning effect, an early step in understanding planetary shape. He explored how objects behave when they collide, building on the ideas of Galileo and Descartes and describing laws of impact between moving bodies. Huygens explained that if two equal bodies crash, they trade speeds, and if one hits a still object of the same mass, it stops while the other moves. These ideas hinted at a deeper rule, the conservation of energy, though real materials were not perfectly elastic and lost some energy in collisions. Isaac Newton later calculated how different materials reduce velocity on impact, measuring wood, glass, cork, and steel in his groundbreaking Principia. Another revolution came through experiments with air pressure, led by scientists like Torricelli, Pascal, and Otto von Guericke. Pascal declared that a vacuum could exist, but many still believed nature hated empty space and even claimed no force, not even angels, could create one. Otto von Guericke silenced skeptics with an experiment involving two metal hemispheres, sealed together and emptied of air. Before the emperor of the Holy Roman Empire, 16 horses failed to pull them apart until a valve was opened and air was let back in. This dramatic moment proved that air pressure was real and powerful, and Guericke became known for making science understandable to rulers. He collapsed metal spheres by removing their air, proving atmospheric pressure with a loud, shocking sound. By emptying one of two equal globes, he made the other fall, demonstrating that air has measurable weight. Though his vacuums were not perfect, he showed that in a vacuum, flames die, animals faint, and sound disappears, setting the stage for future discoveries. He used vacuum suction to move water and lift weights, laying early groundwork for machines like the steam engine. Though he delayed publishing his work, he shared it with Jesuit Professor Caspar Schott, who printed it in 1657 and inspired further discoveries. One man deeply moved by this work was Robert Boyle, an English scientist born to wealth but dedicated to knowledge and faith. He built a laboratory at Oxford and joined a circle of scientists who would one day form the Royal Society. Boyle was deeply religious but also passionate about experiment, believing that true science did not conflict with divine order. Together with Robert Hooke, he designed a new air pump to explore the weight, pressure, and behavior of air. He showed that a barometer AS mercury column is held up by air pressure and that feathers fall as fast as stones in a vacuum. He proved that light travels through a vacuum, but sound does not, confirming that air carries sound but not light. He showed that living creatures need air, famously saving a mouse from suffocation by letting air back into the vacuum chamber. Boyle's work inspired Guericke to improve his own pump and led Christian Huygens to explore similar experiments across Europe. Boyle went on to study light, crystals, heat, and water pressure, searching for the hidden laws behind everyday things. In 1662, he announced a law. As the volume of a gas decreases, its pressure increases. Today we call this Boyle's law. Hooke had reached the same result earlier, and in France, Edmond Mariotte did too, though Europe often called it Mariotte's law. Boyle also explored heat, calling it the motion of tiny parts inside matter, not a substance, but movement itself. Hooke said all matter vibrates, and that fire and flame come from air reacting with heated material. Cold, he said, was just a lack of motion. Experiments in light were equally bold, melting metal with focused sunlight and using ice to explode gunpowder with concentrated rays. In the physics of sound, scientists showed that plucked strings vibrate not just as a whole but in parts, creating overtones and resonance. In 1711, the tuning fork was invented, helping musicians and scientists measure pitch and vibration with precision. Scholars across Europe attempted to measure the speed of sound, and Boyle came closest, calculating it at around 1,126 feet per second. They also learned to use sound to measure storm distance by watching lightning and timing the thunder that followed. Then came the question, what is light? Hooke believed light was a motion of particles inside glowing objects, just faster than heat. For centuries, many believed that light moved instantly, too fast to measure. But in 1675, Danish astronomer Olaus Romer proved light had a finite speed by watching Jupiter's moons and how their eclipses changed with Earth's position. From these observations, he estimated light's speed at 120,000 miles per second, much lower than today's estimate of 186,000. Another mystery was diffraction, the way light bends around objects or spreads through tiny holes. Jesuit scientist Grimaldi saw that light spreads like waves, supporting a theory first imagined by Leonardo da Vinci. Hooke agreed, but it was Huygens who explained this idea fully in his treatise on light, describing light as waves moving through an invisible medium called ether. Huygens explained reflection, refraction, and translucence using this wave theory, though he admitted it couldn't explain polarization. Newton rejected the wave theory and supported a corpuscle idea, that light was made of particles, not waves. Electricity. Electricity was less developed at this time, but curious minds were still at work. Guericke created friction-based electricity using a rotating ball of sulfur that attracted feathers and paper. He observed repulsion, too, watching a feather jump between the charged ball and the floor. He showed electricity could travel through linen and that objects could be charged simply by being near other charged items. Francis Hauksbee advanced these experiments by creating electric sparks inside glass, bright enough to read by. Others began comparing electric sparks to lightning and thunder, ideas that would later be confirmed by Benjamin Franklin. Piece by piece, the physical world began to open, not as a place of magic, but of measurable wonder. They didn't conquer empires or command armies, yet their quiet discoveries reshaped the world. From the ticking of a clock to the spark of electricity, they revealed a universe ruled by law, not chance. In today's world, physics continues the journey those early minds began. With powerful particle accelerators like CERN's Large Hadron Collider, scientists now smash atoms to reveal forces hidden deep within the fabric of reality. Discoveries like the Higgs boson, the particle that gives mass to everything, confirm theories first imagined decades ago. Meanwhile, quantum mechanics reveals a world of strange behaviors, particles that can be in two places at once, and forces that act across vast distances instantly. These ideas are not just theoretical. They fuel technologies like lasers, MRI machines, GPS systems, and quantum computers that are already reshaping the future. At the cosmic scale, physics also stretches our minds across time and space. Space telescopes like James Webb now peer into the earliest light of the universe, revealing galaxies formed just a few 100 million years after the Big Bang. Physicists grapple with dark matter and dark energy, invisible forces that make up over 95% of the cosmos and still elude full understanding. From the dance of atoms to the drift of galaxies, physics remains our language for decoding the universe. And just as in the 1600s, today's physicists do not end wonder. They turn it into deeper, more precise questions. Thank you for watching Uncover Time. If you believe in the power of history to inspire, like, share, and subscribe for more journeys into the minds that changed our future.